Hello there. In this video, I'll try to explain how to compute the Fourier transform in MATLAB to plot the magnitude spectrum. Magnitude spectrum is a plot which displays the frequencies which are present in a time domain signal. It has frequency values on the horizontal axis and amplitude values on the vertical axis. For example, if I have a time domain signal x, which is a simple sine wave having a frequency of 50 Hz and an amplitude of 10, its magnitude spectrum will look something like this, where on the 50 Hz I'll have an amplitude of 10. Now this is an ideal plot. Whenever you compute the magnitude spectrum of any signal, it won't be perfect. Now let's start with the computation of magnitude spectrum. First of all, you have to use the FFT command of MATLAB to compute the Fourier transform of your time domain signal. The next step will be to compute the absolute of this Fourier transform, because the values will be complex, and in the computation of magnitude spectrum the complex values are not required. Given below is the Fourier transform, absolute Fourier transform plot of the signal that I have shown you before. It is anything but what we want. It is quite weird. The vertical axis doesn't make sense, also not the horizontal axis, and also we are having two peaks where there is only one frequency present in our signal. So we will polish this plot into our desired format in the following steps. Before moving further, I will talk about the symmetry of the Fourier transform. That is, for the real valued signals, the Fourier transform is symmetric, and almost half of the values are duplicate. Given below is the absolute Fourier transform plot of a random signal. If you notice, it is symmetric around the sixth sample, which means that the value 5 and 7 are equal. The samples 5 and 7 are equal, 4 and 8 are equal, 3 and 9 are equal, and 2 and 10 are equal. Since the length of this Fourier transform is even, which is 10, there are two samples which have no duplicate values, and that are the first sample and the sixth sample. However, if the Fourier transform length is odd, then there is only one sample which has no duplicate value, and that is the first sample. In this example, the samples 6 and 7 are equal, 5 and 8 are equal, 4 and 9 are equal, 3 and 10 are equal, and 2 and 11 are equal. The next step is to drop the duplicate samples, but this comes with a consequence, because each value, each sample in the Fourier transform represents the magnitude of specific frequencies that are present in the signal. So dropping the duplicate samples means that the half of the magnitude of the concerned frequencies will be gone. So to balance this consequence, you have to multiply all the samples whose duplicates you have dropped by 2. The next step is to normalize the magnitude. By the virtue of the Fourier transform formula, the magnitude of every sample of the Fourier transform gets multiplied by the input signal length. So to unveil the true magnitude of all the frequencies, you have to divide all the samples by the signal length. The last step is to establish the frequency axis. At this stage, all the samples in our magnitude spectrum have their true amplitudes, but if you notice, the horizontal axis doesn't make sense. We expect the frequency values here in Hertz. So to establish the frequency axis, you have to first remember that the first sample of the magnitude spectrum represents a frequency of 0 Hertz, and the last sample of the magnitude spectrum represents a frequency which is half of the sampling rate. To establish the frequency axis, you have to have an idea about the FFT resolution. Um, FFT resolution defines the frequency gap between the two consecutive Fourier transform values. It is calculated by dividing the sampling frequency by the FFT length. Let's understand it with an example. Let's say we have a sampling frequency of 200 Hertz and an FFT length of 10. So it's the FFT resolution comes out to be 20 Hertz per step. Now, if I use this FFT resolution to establish the frequency axis of the magnitude spectrum, which is present on the right, I can do it as the first sample will represent a frequency of 0 Hertz, and the next sample will represent a frequency which is 20 Hertz greater than the previous one. So you have to take a step of 20 Hertz, right? So the next sample will be 20 Hertz greater, which means 20 plus 20, 40, and similarly you get 60, 80, and in the end, the last sample of the magnitude spectrum will represent a frequency which is half of the sampling frequency. Here you can see the sampling frequency is 200 Hertz, so it will represent a frequency of 100 Hertz. So that's all. It is the magnitude spectrum of a signal. Now let's move toward the code. I have two examples for which I will plot the magnitude spectrum. In the first example, I have a signal which contains a DC value with an amplitude of 5 and two sine waves, one with an amplitude of 1 and frequency of 50 Hz and other with an amplitude of 10 and a frequency of 100 Hz. I have chosen its sampling frequency to be 2048 Hz. The second example is of an audio signal which contains human voices and it has a sampling frequency of 48 kilohertz. You can figure out the sampling frequency of any audio in VLC media player by pressing Ctrl J, and as you can see it has a sample rate of 48 kilohertz. For the computation and plotting of the magnitude spectrum, I have made this function which follows all the steps which I have already explained in the presentation, so I won't go into its details. Now let's run the main file. Here the first figure displays the magnitude spectrum of the first example, where we can see three peaks. The first peak is for the DC value, which has an amplitude of 5. The second peak is for the sine wave with the frequency of 50 Hz and an amplitude of 1. And the third peak is for the sine wave with a frequency of 100 Hz and an amplitude of 10. The second figure displays the magnitude spectrum of the second example, which contains human voices. If I zoom it in, you can notice that the dominant frequencies are below 1000 Hz, and this is how the magnitude spectrum of human voices is supposed to be. So that's all. I hope you have learned something from this video. If you have any questions, feel free to drop them in the comment box. And thank you very much.